the first thing, and the next thing is I guess the pro tip is that I probably should have combined them into a single slide, but here is a less PLE but more formal. This describes our attempt to build a better formal verification infrastructure for verifying high-performance caches. As with all the grad students in the room, I chose to do grad school because I wanted to solve this Intel problem from almost 30 years ago, the Intel FDiv bug. That is everyone's fantasy. I want to solve a problem everyone's so for. And here we characterize the bugs you would run into when you're designing a new CPU and bringing it up on FPGA prototyping platforms. You have so first the y-axis is on a log scale. So you have different kinds of bugs that would manifest in different parts of your CPU design. You have bugs that would manifest in your CPU pipelines. For example, you may execute one more or one less instruction because your branch misdict signal was mishandled. And you can have bugs in the cache, and usually the curve is like this. So the time when the bug manifests and the time so this bug to error cycle describes the cycle where the bug manifests and the cycle when it actually triggers a fatal software error. So what that means is that if you have like a branch misdict error, then it's actually very easy to crash your entire software system because those instructions, everything is in register only, and you need to use them right away, and soon it will be unrecoverable, and you will get a oops in Linux boot process. And on the other hand, you have those nefarious cache bugs, and they are extremely hard to locate and find, and even if you found them in simulation, often it takes like tens of millions of cycles to go through the waveform to find out where the bug happened, because you can write a value and you can write a wrong value to a place and don't use it for a couple million cycles. That's like totally normal. So the unfortunate byproduct is that your happiness life when you encounter this bug decreases exponentially and completely vanishes when you have consistency or atomic bugs on your FPGA, and happiness is one of those things you would rather leave a little in your life. So that's why we're developing a reusable and composable formal verification framework for caches. We take a layered approach to verifying different aspects of your caches. Well, for starters, your read and write operations must be correct, otherwise coherency is kind of like irrelevant. Also, you kind of need the instructions you need for locks, and LR and SC usually have specific microarchitecture structure to support them. You also need to, if you want to make this multi-core, you also need to think about cache coherency. And last and not least, everyone's favorite thing to verify, memory consistency. Which definitely nobody wrote RTL that has consistency bugs before, and when we get a proof, the goal is that the proof must converge on real-world designs. That means in a reasonable amount of time, it must either give a counterexample or have a conclusive proof that your design has no bug, and it also needs to be sound. And here I'm going to talk about what sound means compared to some of the prior works. So a lot of the prior check works, they work by generating litmus tests, and they are sound in the way that every bug they find is indeed a bug. But when they say there is no bug we found, that doesn't mean that this is definitely bug clean. That means like for these complex litmus tests that we have uncovered no bug. Whereas this work and the Auto-SVA work is more on the side of, you may under-constrain your design and find bugs that are actually not bugs, but when it says that there is no bug, there is really no bug. So for background, we use you may want to look at BMC, abstraction, induction, reachability analysis, all those things, because unfortunately Jasper is kind of a black box, and you need to basically kind of understand these techniques to understand how it works. And there's also a technique in parallel, which is STE, which is also interesting to look at. So the idea here is that we want to under-constrain our verification environment as much as possible. And before we start, I'm going to talk about the most important thing in formal verification, which is covers. Covers are fundamentally the thing that protects yourself from shooting yourself in the foot if you over-constrain the design. Thus, you say there's no bug, but actually there is. You just can't generate them from your verification environment. And all the covers are automatically generated in addition to all those assertions and assumptions. And we actually put more, actually much more covers are generated in the final product. So all our assertions, so basically everything we do is symbolic, and none of the things are deterministic, because if you want to sustain outstanding requests, then you don't really have a fixed latency of how things will happen. That is tightly coupled to your LLC architecture or your CPU side microarchitecture. So basically, we assume that all the signals can fire at any point unless it's not realistic. For example, the LLC won't reply some data to the cache until it is requested. So the heart of the input to our framework is a microarchitecture table where where each column describes a control path for different types of requests. For example, these from top to bottom, there's read hit, read miss, write hit, and write miss. And each row describes a different stage, pipeline stage in our microarchitecture. And you have all those signals in the middle that annotate what signals could appear at which stage, and the interface between this stage and the next stage. For example, VR stands for valid read interface. We also have valid only interface, and we also have these signals like kill if you have a branch mispredict and you need to kill this transaction, or you have a replay signal from the cache to the CPU that basically says, oh, by the way, all my buffers are full and I can't really handle this outstanding miss anymore. Please send it back some later time. And we also provide you with an add signal that basically enables you to link to an external embedded SVA property module or checker to constrain some specific RTL signals, either to over constrain some parts of the design or under constrain them. Also for designs where we don't provide, you didn't swap in the primitives we provide. We also all the VIPs between cache CPU interface and interfaces between stages and the LLC, which is TileLink, are reusable. They are generic, and they don't make any assumptions about your microarchitecture, such as latency to reply or how many outstanding misses can you sustain, these sorts of things. And automatically, safety and liveness properties are implied, and by this I mean that you would assume that for a cache, if an instruction enters the cache, if a request that enters the cache that doesn't get killed, then it will exit at some point in the future. And also you assume that it makes forward progress, which we're going to show in a minute is not always the case, even in untrivial examples. And this table will be elaborated to stage-specific properties and as well as interstage properties. And one of the reasons we do this is that one of the reasons we can do this is that although there are multi-cycle relationship between these properties, all of our initialization states are symbolic. So as we're going to show here, we basically swap all these buffers and state element control structures with symbolic initialization, so that when you come out of reset, instead of having all your cache rates clean, you actually initialize everything into an arbitrary state. And so the proof later is on arbitrary address, arbitrary data, and arbitrary different address pairs that you're going to check for instead of for a specific pair, and that is tremendously helpful in reducing the complexity. And we also do model refinement for consistency properties. So the idea here is that the model itself is very complex, hard to get right, and usually takes more than a PhD to understand them fully. And a lot of reordering is going on at microarchitecture level. For example, your write buffer, your load queues, all those things can potentially disrupt your the order of requests flowing through the pipeline. And you also need to handle specific cases, like you can have a flush in the middle of nowhere coming up. So the way we do this is that we iteratively, so we basically check if you want to check it adheres to some consistency level, then you basically check that it will be able to reorder some of these rules, while it will never make a reorder that complies with some of the weaker rules. And ironically, we use GNUM4 because we value readability, and using another macro system on top of SVA system verilog macros allows us to make all the properties names readable. And we actually we perform our evaluation on this high performance non-blocking data cache for a superscalar CPU where nothing blocks. Literally nothing blocks until you have 32 misses. And we have uncovered 9 bugs with different things. And the thing we do is our proof actually converges within an hour, and we have a reusable library of abstracted model for common cache performance. And here's some future work, and thank you so much for listening.